Hi students, today I'm going to explain the problems related to bridge rectifier, which is same as I said or as I explained in previous lecture in full wave and half wave rectifiers. I'm Dr. B. Ravi Kumar, Associate Professor, Department of EC, Institute of Aeronautical Engineering. So let us see now the problems on bridge rectifier. As we know that the one of the most important rectifier, which is which was used in many applications in a real time, uh, power supply modes or any wherever required the DC supply. So this bridge rectifier has we had preferred among the half wave rectifier and full wave rectifier. Basically, half wave rectifier is impractical, it is not at all useful for practical application. And coming to the full wave rectifier, when compared with the full wave and the bridge rectifier, full wave rectifier requires center tap transformer. So it is a cost of very high. The cost was very high compared with the bridge rectifier. Let us see that full wave rectifier center tap transformer is cost of 200 rupees, for example. The same the bridge rectifier with a normal transformer with 50 rupees, plus in a full wave rectifier require 4 diodes. Each diode is a cost of 5 rupees, nothing but 10 rupees. And in the bridge rectifier we require 4 diodes, means 20 rupees. So when take this all, so in full wave rectifier you will need 210 rupees to design this simple diode with a transformer, and it requires only 70 rupees. So that much of economic this bridge rectifier was. Anyway, coming to the problems, the bridge rectifier. Remember students, in the bridge rectifier they use normal step down transformer. In the normal step down transformer, whatever the primary voltage V1 is given, like 230 volts, 50 hertz signal, the AC supply is given, and the turns ratio, primary and secondary turns ratio, you will directly find out the secondary coil voltage with the relation V2 by V1 is equal to N2 by N1. We already know that V2, like V1 primary voltage and turns ratio, N2 by N1 into supply voltage, or V1 or VA. So directly we can take that V2. Once we know the V2, then the maximum voltage need to be find. Vm is equal to root 2 into V2. That is enough in the bridge rectifier and a half wave rectifier. The only focus more on the center tap transformer. Again, that V2 again divided into 2 parts in the center tap. That is the only difference. Once you are aware of this thing, how to find out the Vm, then it is very easy to find out the problem. Let us see. Read the problem now. A 230 volt 50 Hz voltage is applied to the primary of 4:1 step down transformer. They have given 230 volts, 50 Hz AC signal, AC input voltage, and transformer is a step down transformer with a 4:1 turns ratio. Okay, used in a bridge rectifier having load resistance 600 ohm. 600 ohm. Assume the diodes to be ideal. If it is not ideal, we need to be considered that internal resistance of diode, internal resistance of secondary coil. So then find out the DC output voltage, DC power delivered to the load, peak inverse voltage, output frequency. If it is required, we need to find out the ripple factor, everything. So the given data, given data for this problem is primary voltage or AC input signal primary voltage is 230 volts. Transfer ratio N1 by N2, like N1 is to N2 is equal to 4:1. And 4 diodes and load resistor is 600 ohm. Find out the DC voltage, VRMS voltage. If you want to find out ripple factor, and DC power delivered to the load, PDC. If you want efficiency, we require PSC, and then efficiency, and then peak inverse voltage, and then frequency, output frequency. Let us see one by one. How to find out the first parameter, DC voltage or average voltage for bridge rectifier. Similar, we know that formulas, that VDC is equal to Vm by pi. What we require? Vm is required. Where will we get Vm? Vm get from secondary voltage V2. How to get V2? We know the known parameters V1 and N1, N2. So the relationship between consideration and primary and secondary voltage is V2 by V1 is equal to N2 by N1. V2 is equal to N2 by N1 into V1. N2 nothing but 1, N1 is nothing but 4 into V1 is equal to 30 volts. You will get 57.5 volts. It is equal to 57.5 volts. Then once we know the V2, what is the maximum voltage available at a secondary coil with the edge of secondary coil, and also the available to diode is the Vm is basically root 2 into the RMS voltage of secondary coil voltage, which is equal to V2. We can call it as, what we call V2. We call it as V2. So we know already find. Just now we find out V2 multiplied by root 2. Root 2 into V2 nothing but 57.5. Now can we get the Vm? Yes. Vm is equal to 81.3. If you calculate it, you will get 81.3 volts. This is called maximum voltage switch to diode. With this maximum voltage, the secondary coil voltage, when it is switched to diode, then it is operated like forward bias, reverse bias, and also it will be act as a rectified during the up cycle, pulsed up cycle. Two diodes gets on during the negative up cycle. Two diodes gets on, so that you will get rectified output in the bridge rectifier. So this is the Vm. Once we got Vm, then we can easily substitute that actual. What do you find? We need to find VDC. VDC is equal to, the formula is 2Vm by pi. This is the formula already derived. By the mathematically, we can take that sinusoidal input, S input signal, and take the definition of average value of the signal, of the input signal, and what is the output delivered DC voltage. Then you will get 2Vm by pi. If it is ideal, it is 2Vm by pi. If diodes are practical and secondary internal resistance, then we need to subtract the drop from this 2Vm by pi. So now 2 into Vm, you got 81.3 divided by pi. Then you will get the answer VDC. The DC voltage or average voltage, you will get 51.75, approximately 52 volts. Maximum is 81, and when we pass it and reach to the load, the DC voltage is 52 volts. Then actually the problem in the problem it is not given, then we require, if you wish to find VRMS, then we will get, what is VRMS? Maximum voltage by root 2 for full wave and half bridge rectifier, Vm by 5, Vm by 2 for half wave rectifier. So Vm by pi, Vm by root 2 is nothing but 81.3 for Vm divided by root 2, you will get 57.5. Then ripple factor. Basically the ripple factor is nothing but the definition of ratio of VRMS by VDC, or in other words, another equation, square root of VRMS by VDC whole square minus 1. If you substitute all the parameters known, so once you substitute all the parameters like VRMS 57.5 divided by VDC 51.75 whole square minus 1, you will get 0.5. Ripple factor is 0.5. When compared with the half wave rectifier, we got 1.21. That will, we got reduced in the ripple factor. Basically, what people the designers expected that the ripple factor goes down when compared with this half wave to full wave and bridge rectifier. So in the bridge rectifier, full wave bridge rectifier and the full wave rectifier, the ripple factor is got reduced. What does it mean? The reducing of ripple factor means that AC components presented in the rectified output gets reduced. So as keep on reducing the ripple factor means keep on improving the rectified DC voltage across the load. Then next parameter, DC power delivered to the load. DC power delivered to the load. PDC. How can we get the PDC? We know the formula VDC square by RL. All are given. So VDC, we have given VDC 51.75 whole square, square divided by RL 600. You will get the answer 4.46 watts PDC. If you wish to find efficiency, we need also find out the VAC, the AC power given to the rectifier. The PS is nothing but VRMS square divided by RL. You will get VRMS square 57.5 whole square divided by RL. You will get the answer 5.51. So efficiency is equal to efficiency eta is equal to PDC by PSC into 100. So PSC you will get to 5.51. PDC 4.46 watts divided by 5.51. You will get 80.9 into 100. You will get 80.9. Efficiency, 80% efficiency. Then peak inverse voltage. This peak inverse voltage is Vm only. What is Vm? How much Vm it is? 81.3. 81.3 volts. And what is output frequency? Basically, why it is called Vm? If you see this diagram, so whenever this VM voltage positive, D1, D3, D3 are on. Whenever these two are on, short circuit, and these are off means open circuit. When these two are open circuit, okay, so this VM, whatever the VM available, here it is available VM. So the same VM with respect to ground, if they are in parallel, these two are short circuit. So whatever the VM here also VM. So VM with respect to this short circuit, VM with respect to the short circuit means whatever the ground, it is ground also. So these two are parallel. A, B points are parallel. A, B, C, D are parallel. In parallel, voltage is same. The same VM voltage available across the reverse bias PN junction diode. For example, some other case during other positive cycle, these two are open circuit. Whenever these two are open circuit, that VM voltage with respect to this point and VM voltage with respect to this voltage with respect, this VM voltage here. Now in this case, this VM with respect to ground and same voltage, like this same voltage VM voltage. If it is short circuit, same VM voltage with respect to ground. VM voltage. So in parallel, voltage is same. So during positive half cycle, during negative half cycle, in both cases, only VM is existed. The peak inverse voltage across the reverse bias PN junction diode is VM only. That's why peak inverse voltage is 81.3. The frequency, output frequency is equal to 2 into input frequency. Basically, this is the input signal. This is the input signal. This is the output signal. So the frequency on full cycle time period is T capital T. But whereas the output frequency T by 2 only. When if you convert it to frequency, F is equal to 1 by T. Okay. So F is equal to output frequency, F is equal to 1 by T by 2. If you measure in frequency, it is F, T is equal to 1 by F, T by 2 is equal to 1 by F in frequency, T frequency like T time, which is equal to 1 by F. When in the output, rectified output, it gets only the frequency measured in every cycle. So then we take that frequency, the time is gets off, that means frequency doubles. So 2 into F. So 2 into F5. So this is equal to 2 into 50 hertz. You will get 100 hertz. This is the way we find out all the parameters. Once we get the V2, we find the VM. Once we find the VM, substitute in the VDC, we will get the VDC and the VRMS. These two parameters substitute in the ripple factor, you will get a ripple factor. And once we know that VDC, VRMS, we substitute in the efficiency, PDC by PAC, you will get efficiency and peak inverse voltage and output frequency. If you see this problem, it is a rectifier, bridge rectifier. In this case, I am taking two bridge center tap transformer, full wave rectifier and a bridge rectifier. What will be the DC voltage delivered across the load? The same input, 230 volts, 50 hertz, 5:1 turns ratio, 5:1 transformer. Here also bridge rectifier, 230 volts, 550 hertz, 5:1 transformer, and then load 100 ohm. So when we compare this full wave bridge rectifier and full wave rectifier and bridge rectifier, Figure 1 and 2 shows the center tapped and bridge rectifier circuit having the same load resistance and transformer transfer ratio. The primary of each is connected to 230 volt 50 hertz. Find the DC voltage in each case, like full wave and bridge. Peak inverse voltage for each case for the same DC output. Assume the diodes to be idle. Let us see. In this case, we know that already we find out how to find out the V2 output voltage. Secondary coil voltage is equal to N2 by N1 into V1, which is equal to 1 by 5 into V1 is 230 volts. You will get 46. So you will get 46. What is the maximum voltage? Vm root 2 into 46. You will get 65 volts. Maximum voltage appearing across the half secondary winding. Why I am taking half secondary winding? In this case, you will get V2. Again, this center tap, due to center tap, that V2 divided by V2 by 2. That voltage across here. And half that again V2 by 2 voltage again remaining V2 by 2 V2 by 2 voltage across this end. So we need to find out Vm by 2. We'll get 32.5 for this only full wave, center tap full wave rectifier. That is what actually Vm. This is actual Vm. It is not secondary voltage maximum secondary voltage, but actual Vm reached at the edge of each edge of the secondary coil with respect to center tap. Vm is equal to 32.5. That Vm is substituted in the formulas. So DC output voltage VDC is equal to 2 Vm by pi. 2 into 32.5 divided by pi is equal to 20.7. Similarly, the same Vm voltage, actual secondary voltage, maximum voltage across secondary coil is 65. No need to divide by 2 because in the bridge rectifier we use normal transformer. So the same 65 voltage delivered to the diode and then we will get the DC voltage. So Vm voltage 65 across the diode. Then what is the formula for DC output voltage for the bridge rectifier is 2 Vm by pi. 2 into 65 by pi, you will get 41.4 volts. So same network, same input voltage is same, transfer ratio is same, load resistance is same, but DC delivered to the load, DC output voltage across full wave rectifier is 20.7, whereas bridge rectifier you will get more, 41.4 volts. Okay. If you see the other case, input voltage is same, transfer ratio is same. Transfer ratio. If you change the transfer ratio to get the same DC voltage, you will get the same DC voltage. What will happen? Okay. Now I am taking the transfer ratio change to get the same DC voltage. RMS voltage, secondary voltage 230 into 1 by 5 is equal to 46 volts for this transfer ratio. And secondary coil voltage, RMS voltage 23 for this ratio, transfer ratio 10:1. Then what is the maximum voltage across secondary coil? 46 into root 2, 65, and divided by 2, you will get 32.5 for the maximum voltage. Maximum voltage across this node. Maximum voltage across these two nodes, 32.5. Similarly, other side of the bridge rectifier, what is the maximum voltage across secondary voltage? Vm is equal to 23 into root 2, you will get 32.5. Okay. So what is the peak inverse voltage now? Here it is peak inverse voltage is 2 Vm 2 into 32.5, whereas in bridge rectifier peak inverse voltage is Vm only 32.51. So here it shows that these two figures shows that the same secondary coil voltage, maximum voltage, DC voltage. Here it is, the maximum voltage reached to the diodes is 32.5, But whereas in peak inverse voltage, the peak inverse voltage across full wave rectifier is doubles 32.5, doubles which is occurred in the bridge rectifier VM 32.5 only, whereas in full wave rectifier you will get 2 into 32.5. That much of maximum inverse voltage across the diode means it bears that voltage. So peak inverse voltage is different in this example. In this way, we find the problems on bridge rectifier by considering the given data. This is the question bank. You go through that question bank and see that problems. And then this is the electronic device and circuit by Salio Hanna. We'll take, if you want more problems, you will go through that one. And this example, second example taken from this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.